Okay, so we are continuing with linear MMSE estimators. So we are dealing with almost like the same problem, but this time the problem is complex valued. Let me see. So observation vector axis, there is a P times a C random variable plus this is N. So P is known vector. Okay. C is desired random variable. But unfortunately, let's say that this is complex valued. Well, why it's unfortunately? Because I know the real valued derivation. I have no idea about complex valued case, and I will derive the complex valued case immediately. And N, so uncorrelated noise, or let's say just noise, I think it's clear. Noise, let's say vector. Okay, so this bar and there is a tilde at the bottom to indicate that that's a random quantity. So then this is also a random quantity, but this will be my observation, okay? So over here. So this is non-random, not random, but we know this. So previously in the earlier example, P vector was just one vector, okay? So this is all ones, C times 1 plus noise. Right now it's maybe, a complex valued vector. So this is noise vector. Again, noise may have, or let's say it has complex value. It has a real part and imaginary part according to a distribution, okay? So I end up with this. So the question is, again, estimate C. Okay, C. Using with linear minimum mean square error estimator. Okay, the same problem. So how can I handle this? Now I would like to discuss, well, the complex valued case first. Complex valued case for linear minimum mean square error estimator. Okay. So how should I start? Now I have some weights and now I have a desired random variable y. This is, okay, let me write y hat. Okay. So this y hat is weights times x. Okay. Again, I'm not repeating. X is the observation vector, like over there. So y is the desired quantity, and this is the estimator. But please be careful. Now I have Hermitian of weights over here. So this is h. Hermitian of the weights. Okay. Now I would like to take the derivative of this, or the gradient of this, with respect to conjugate of the weights. Okay. So previously we have discussed this a little bit. So what do I mean by this? I would like to evaluate the following. Partial derivative with respect to omega 1 conjugate of this j function. Or let me write j over here. Partial derivative with respect to omega 2 and partial derivative with respect to omega n of this j function. Okay. So weights are complex valued. Previously we had real valued case and we were taking again derivatives and we end up with these two results. Now I will do the same thing, but this time for complex valued case. Now if I write this over here, well, as, let me define this as my E. So this is my estimation error. Again, it's a complex quantity. So then this is nothing but expected value of E times E conjugate. Am I right? Okay. Expected value of E times E conjugate. Now the question is, so how can I take the derivative with respect to W1 conjugate over here? So again, what is E? Where is my blue marker? E is over here. Writing this one more time. Y minus W Hermitian times X. Okay? What is the conjugate of this? So this is Y conjugate minus W transpose times X conjugate. Am I right? Because if I take the conjugate of this, Hermitian becomes transpose because two conjugates cancel each other and I have conjugates at the other variables. Okay. So I should take the derivative of this so this differentiation will move in and I should take the derivative of this. So where do I see, let's say let's say 1 conjugate. So I see W1 over here, but there are no W1 conjugates in this term. Okay. So I see W1 conjugate over here and it's multiplied by X1. Am I right? I see something like that if I do this calculation. So if I do this, then I get this. So this is expected value of, so this. Now this gradient vector with respect to conjugate variables of E conjugate. Okay. Gradient of this. So nothing new. Only thing is now this gradient is moved inside of this expectation. Now what else? Then expected value of, so I see that this is gradient of E conjugate goes out, gradient of E. So what do I mean by this? Now I should take the derivative of, let's say with respect to W1, one more time, W1 conjugate, of these two terms. But you see that over here, there is no W1 conjugate. There is W1, but not its conjugate. And in this calculation, this is a method, W1 and W1 conjugate are considered as independent variables of optimization. So W1 conjugate only appears over here. W2 conjugates only appears in this term. Okay. So then, what is this? If you check this, so then derivative of this term only, with respect to, let's say, again W1 conjugate, you get X1. With respect to W2 conjugate, sorry, you get minus X1, you get minus X2, minus Xn. So you get this, expected value of E conjugate times, there is a minus X vector. Okay. So negative of this X vector. If I take this derivative, I get this. Okay. So I will take this derivative and of course equate it to 0. 0 vector. Then, let's go. I end up with this result. Error conjugate times X vector is equal to 0. Okay. So this is our final result. Error conjugate, so this is not error conjugate times X vector is equal to this 0 vector. So this is again our orthogonality principle. And we have exactly the same result without conjugates in this real valued derivation also. But I want to calculate, this equation at the end. But okay, let's try to do that. So this is then, so what is E? So E conjugate is actually over here. Okay. So let me write that. Let me move this X over here. X. Then E conjugate is, I have written it over here. Y conjugate minus W transpose times X conjugate is equal to 0. Okay. Then, if I okay, so what did I do? I have written actually I have moved this second term to the other side. Okay, so there's x, vector x, times this parentheses, but on the other side without a minus, exactly like that, is equal to x vector times y conjugate. Okay. Again, as you see, our notation is very helpful because I know that x is observation vector, y is desired random variable, it's a single scalar quantity. So this is just inner product of two vectors, this is a scalar, as you see. So scalar times a vector is a vector. If I take the expected value of a vector, I get a zero vector. So again, dimensions can be checked like that. But as you see, this is a little bit strange. But now, I want, well, this is good. This part is ryx. This is my ryx, or rx. I have written it correctly, but say that wrongly. rxy. rxy, as you see. Okay. So this part is done. So how about this part? Now, since this is scalar, can I take the transpose of this? Transpose. Can I take it transpose? So if I take its transpose, what would I get? Okay, so I get this. I have x Hermitian times w. Because if you move this x conjugate transpose is Hermitian, w transpose is w. Okay? Then this is then equal to, because this is a scalar, its transpose is equal to itself. Then this is equal to expected value of x times x Hermitian times w. Okay? This blue box is equal to that. Now I will take this, w is not a random quantity, I can take it out of expectation. Then I will get the following. Rx times this w vector is equal to ryx. Okay? So what is this? One more time. This is expected value of x y conjugate. This is expected value of x Hermitian. Okay? By definition, and that is it. Okay, so almost like that, x, y, okay? Almost like that, but a little bit different. Let's also calculate this, linear minimum mean square error value. Let me use this. Let's also calculate relation. So this is J minimum for this optimal W's. That's this set, optimal W's. Okay, OPT, let's say, OPT is equal to expected value of, this is this, error random variable, magnitude square. But this is error of optimal estimator. Okay? Then this is equal to error times, so this is, let me write it like this, this is error conjugate times E. So this is error conjugate times, so what is this? E is equal to this. Okay? So E is equal to y minus w Hermitian x. So this is desired quantity. This is its estimate. But again, I'm producing this estimate with w Hermitian. This Hermitian is actually quite important in this derivation. Okay. Why I have this Hermitian? Well, you will see. It will be more practical later on. Okay. So if I have something like that, then this is equal to expected value of minus so these are all scalar. This is a vector, this is a vector, but due to the orthogonality condition, this is this condition. Optimal weights satisfy this, optimal error then satisfy this orthogonality condition, so I end up with this. So error conjugate is again over here. Okay, expected value of y magnitude square minus W transpose times, this is x, this is vector, x conjugate y. Okay. So, one final step, this is this, minus, I have, let me see, W transpose over here. So if I take this, if I take the, let me see. So I want to use this exactly, Rxy. So this is, okay, W transpose times Rxy with conjugates, okay? Rxy with conjugates. So, okay, then I'm going over here. So this is expected value of y square minus, now if I take the transpose of this one more time, Rxy permission times, this is W, okay? If I take the transpose of this, so again, so these are transpose of each other. These are transpose of each other, okay? Okay, then one more step, maybe this will be useful. Expected value of y square minus Rxy Hermitian. So what is this? W Rx inverse Rxy. Okay. This looks like a complicated calculation, but as you see, we will be doing this calculation only once. So this is our linear minimum mean square error estimation result for the complex valued case. So at the end, I have written this optimal W expression over here, OPT. This is the optimal W expression from here. So similarly, this one, if I write this for the real valued case, expected value of y square minus, again take the transpose of this, Rxy transpose times W, okay, and W is from here, Rx inverse times Rxy, then this is also equal to expected value of y square minus Rxy transpose Rx inverse Rxy. Okay, so this becomes our linear MMSE expression for the real valued case. Okay, so what is the difference? So the difference is, there shouldn't be any difference first of all when y is real valued. Do we see that? If y is real valued, then magnitude square and parentheses square, they are the same. Okay, then Hermitian and transpose, they are the same. Hermitian and transpose, they are the same. So this is the Rx matrix. Well, if it is real valued or imaginary valued, now it is the same Rx matrix. The way you calculate it is exactly the same. Similarly, this optimal weights, this It's the same equation system. So only difference is where you put these Hermitians and conjugates. So if it is real valued, you have a transpose, but a Hermitian over here. Okay. Now, only difference, maybe a significant difference, is over here. Now I have our x and y, cross correlation of x and y. And the second argument, if it is complex value, it has to be conjugated. So in other words, the desired variable is conjugated. Okay? So the desired, not the observation, desired variable is conjugated. Of course, all of this, similarities result when you have this definition. Okay? When you have this definition. So let me then append this with the complex valued case also, with the blue color. Okay. So how do I change this? If this is complex valued, now the change is I have W Hermitian X instead of this. Okay. For the blue. If this is complex valued, then of course this is not the parentheses square, but the magnitude square. If this is complex valued, I have H over here instead of T. Okay. If this is complex valued, I have a conjugate over here. Okay. That is it. For the linear MMSE expression, of course this is magnitude square. I have a Hermitian over here. That is it. Okay. So all of these results, they are extremely similar. So if you know, for example, the real valued case, then extension to complex valued case is very simple. You just put Hermitians and conjugates somewhere and you use the equations as they are. Okay. That is it. So this may look complicated, but again, if you look at these steps, it's actually trivial. Sometimes students are getting confused in this calculation, in this differentiation with this conjugate variable. Please consider it like that. I have n w variables which are to be optimized, but they have real part and imaginary parts. So actually I have two n variables. Okay. So instead of optimizing over real and imaginary parts independently, I'm optimizing the conjugate variable and the variable itself. Okay. But as I have said, it's sufficient to optimize over conjugate variable, and the other will be automatically optimized. As I have said, there is a lecture note on that on Signal Processing magazine on this issue that I have prepared in 2020, I guess, as far as I remember. Maybe 2019. Okay. If that is the case, this differentiation case, then you see that this W and W conjugates appearing over here are independent variables. You treat them as if independent variables. So for the sake of differentiation with respect to W1 conjugate, there is no W1 conjugate over here and there is nothing to do. Okay? It just goes out of here. Okay? That is this, there is no W1 conjugate over here for this one. So E conjugate goes out of this operation and W1 conjugate appears in this bracket. Then you process it and you get your results. Okay, so for the real valued case, we have the derivation. For the complex valued case, did we copy everything correctly? I think we have the derivation. That is it. So in Hayes's textbook, Hayes uses transpose also over here, T, in this linear estimator. And because of that, there are some minor changes, but in this course, I'll be focusing on 99% of the time on the real valued case. So if you need to use this complex valued case, just be careful and you can use these equations if you need them. Now I want to solve this example. So as a case of complex valued estimator. Now this is again a communication kind of system. Well, what do I mean by a communication solution of this example? We go back. Now I will use these results. So what do I have in mind with this example? So P is, in my mind, is some kind of a pulse, okay? So P is maybe I'm sending, some communication pulses like this at every t seconds, okay? So C is the information. So if, for example, you are sending ones and minus ones, then P times 1 or P times minus 1 is sent. Then you are looking whether, the sign of that. You are trying to understand 1 or minus 1 is sent. But there can be some other constellations like QPSK and so on, okay? So for such, then C can be complex valued, obviously. In this, there are many different modulation schemes, and almost all of them, you have, in the constellation diagram, you have IQ pairs, okay? So what should we do for this one? Now, solution for this. So let me look at my notes. How do I proceed? Well, problem is this. Let me see. This noise is given as zero mean, and it has covariance matrix Cn. Okay. Noise vector complex valued. For the complex valued Gaussians, even though we haven't discussed this, there is this notation Cn, complex valued normal distribution. Okay. It's not something very complicated, but let's not discuss it. So covariance matrix is Cn. So this, let's say with the special case, I want to discuss Cn is equal to identity. Okay. I want to discuss this special case first. So what do I need to find? So I need to find this Rx to use this. Okay, so what is Rx? Expected value of P times the C plus N this is a vector. I think random quantities, maybe I don't need to mention them all the time. We know what is random over here. Okay, but this time there is a Hermitian over here, as you see. So we are at this case. Then I have P times P Hermitian times sigma C square. Okay. First term. There are cross terms, but cross terms are, let's say this is also zero mean. Expected value of C is equal to 0, okay? I don't want to worry about means, as I have said, means are not so critical for our purposes. We can always add them later on, as we have discussed last time. So I have P times P Hermitian. There is C square, this constant. Expected value of C square is this then, because this is equal to 0. Cross terms, C times N's, they're uncorrelated. And let me write this uncorrelated. Noise is uncorrelated with C. Okay. So cross terms are equal to 0. Then you have N times N Hermitian. Actually, this is Rn, but autocorrelation matrix of N. But I can write Cn also over here, because it's zero mean, as I have said. Okay. So I want to discuss this, but let's keep this equation. Then, how about this one, right-hand side? R, x, y. Well, y is, for our purposes, just C. Desired variable is C. Okay. Now the observation vector times C. But I should be careful, this is C conjugate. C is complex valued. Okay. Now I have again, this is the P vector, and I have sigma C square, and that is it. Okay. Okay, so what's my equation system? So Rxw is equal to Rxy P times p Hermitian plus, sigma c square plus, let me use the special case over here, Cn is equal to identity. Let me use this identity at this point. Times W is equal to this. Okay. So I can find this W vector immediately over here, provided that I can take the inverse of this matrix. Okay. So how can I take the inverse of this matrix? Okay. So that is the issue. How can I take inverse of this? There is something called matrix inversion lemma. If you are a PhD student, maybe you already know this, matrix inversion lemma. And this is its special case with identity matrix instead of, in general, this is an A matrix. And this is like multiplication of 3 matrices, but this is just rank 1 matrix instead of that. So it's like a very special case of this. Sherman-Morrison lemma that is called for the rank 1 case. So you can take the inverse of this matrix essentially, okay? This Rx matrix. But there is an easier way of doing that. So what do I mean by easier way of doing this? If we follow our linear algebra knowledge, so if this matrix Rx is equal to P Hermitian, sigma c, let me move the sigma c square over here, plus identity. Can you tell me the eigen vectors of this matrix? Or eigenvalues, eigenvectors, okay? Well, how can I, well, let me guess. Let me say that E1 is equal to P. Can this be an eigenvector? So if I multiply Rx by P from the right side, what do I get? I get a P, magnitude of P square, and another P. So you see that, then this lambda 1 is equal to what do I mean by this? Rx times P is equal to, let me multiply this, then sigma c square P Hermitian P plus identity times P, okay? Because I multiply from right by P. But this is equal to magnitude of this, a scalar, magnitude square of this P vector. This is also P vector itself, identity times this. This is P vector. So you see that this is nothing but P vector times 1 plus sigma c square norm. 1 plus, this is eigenvector indeed. Okay, very interesting. So how about the other eigenvectors? Well, since this is a symmetric matrix, I'm sure that there will be n of them. And this is an n by n matrix. And I'm sure that they will be also orthogonal. So how about this? E2 is a vector, let's say, let me write this Q. Let me write Q2, okay? This is a vector where I will write it over here. Qk is orthogonal to P for k is equal to 2 up to n, okay? Then lambda 2 will be equal to just 1. So what do I mean by this? Now Rx times, what was this called? Q2. Second vector is Q2. Okay, so over here, all the differences, instead of this P, I have Q2. Instead of this P, I have Q2. So as you see, if they're orthogonal to each other, like over here, then this is equal to 0. So this calculation is just Q2 then. Okay? If that is the case, okay? If P is equal to Q2, right-hand side multiplied by Q2. So I see that Q2 is an eigenvector of this with eigenvalue 1. So similarly, I can find a Q3. So by, you may say, a Gram-Schmidt operation, you start with this, then you find orthogonal vectors to this one. That is it. You find the eigenvector set. Qn lambda n is equal to 1. Okay. Now you may wonder, okay, we have found these eigenvectors. But is it good for our purposes? It's indeed very good, because as you see over here, I have P. So this is already our, okay, let me write this, then W. This is Rx inverse P times sigma C square, okay? But P is, remember that Rx times P is lambda 1 times P, because P is an eigenvector with lambda 1 eigenvalue. So how about this one? Then W vector is R inverse 1 over lambda 1. So apply R inverse from left. R inverse from left is 1 over lambda 1 times P, okay? Times sigma C square. So this is this. So W vector is sigma C square, and lambda 1 is P square plus 1 times P vector. Okay. So this is the end of this calculation. Okay. So if I have this eigen decomposition, actually, I can decompose this right hand side in terms of eigenvectors and do a very similar calculation. Okay. Please also remember that if A and eigenvector 1 has lambda 1 times E1 relation, then A to the power, let's say A to the power, let's say capital N times E1 as lambda 1 to the power N E1. If capital N is minus 1, you have this result, okay? This is called function of a matrix, okay? Function of a matrix, A to the power N. If you can express your function in terms of a power series, or in this case with the inverses of these powers, then you can always use such a relation. So this eigenvalues and the eigenvectors of functions of matrices can be derived from this original matrix A. Okay, that is our result actually, including this inverse matrix. Okay. So we have found this W. Good news. So what else? Let me erase. Let me see which part should I erase. Now, if I have that, let me write my estimator then. Then C hat, our estimator is W Hermitian times X. Okay. So this is nothing but sigma C square 1 plus sigma C square norm square of this. This is P Hermitian, and this is my X. So this is my estimator. Okay. So this is the end. This is my estimator, and so on. So if you want to analyze this, let's say, so if you want to analyze the statistical properties of your estimate, so insert this model, but X is equal to, say, P, there is C and N. Okay. Then if you want to analyze it a little bit further, let's say, sigma C square P Hermitian C plus I have P Hermitian of N. Okay. So for the sake of this calculation, we know this P vector, so I can calculate this quantity. It's just a number, I can calculate it. So here's another number, I can calculate this one also. This is a random quantity, and this is of course another random quantity. I have two random quantities. So let's see. Well, if noise is very small, meaning that this n vector can be, let's say, ignored. Okay. So what do I see? If that is the case, I see that my C hat is nothing but C times a number. If this is ignored, let's say, noise is very small. This matrix is almost like 0. Cn matrix is almost like 0. So you see that this C hat is this times that times C. So if this factor is equal to 1, it's exactly correct, okay? So this is, you see that it's just a scaled version of C. Is it biased or unbiased? Well, take the expected value of C hat. Expected value of the C hat is expected value of C times this number plus 0, because this is 0 mean, as I have said. And as we have said before, if this is 0 mean, it's again unbiased. If it has non-zero mean, maybe I should add a mean term and do the same calculation again one more time, okay? So let me see, what else do I have? That is it. This is for the analysis part, as you see. Now, this is clear. Maybe interesting part is the application of this complex valued results, and we have made use of these eigenvectors during this calculation because of this rank 1 term and identity matrix. Now, general case. So let's examine the general case with Cn not equal to identity. Okay. So can I also examine this general case? So what do I mean by this? Well, my x of this observation model, P, C, and N. But this one is okay. So what should I do? Well, again, I can derive this. I'll be having this calculation one more time again, but I don't want to drive it again and again. So any ideas what we can do? Now again, I will introduce a new vector. And guess what? This will be the whitening operation output of this observations. Since I know this covariance matrix N, okay, because this is something that I know. This is in the model, observation model. So I know this matrix. This is called whitening. Remember that we have done, computer assignments on that. This is whitening operation. So I'm whitening this noise. So if I do this, then what do I have? Cn minus 1/2 times P plus C plus Cn minus 1/2 times N. Okay. Well, it's difficult to write new all the time. Let me put a hat over here, okay, because it will be easier. So this is my assumed observation. Well, not assumed, but processed observation, let's say. I'm processing it. But this is just like a processing of in our mind, because so this is processed. But if I wish, of course I can implement this operation, but I won't be doing it that way, processed observation. And this is nothing but, the whitening operation. So this is the whitening operator. Okay, then I will call this vector P hat. Okay. Then I will call this vector N hat, and clearly right now I have such a model. X hat is equal to P hat C plus N hat, with N hat is equal to Cn whitening. Okay, I have this. Very good. Now I can use this model. Okay. So I can use this model with our earlier derivation, Cn equal to 1, Cn equal to identity. Okay. So I can use all of my results. Only difference is I should put hats wherever I need them. For example, I should put a hat over here. I should put hat over there, and so on. Okay. That is it. So if I do that, what do I get? So let me keep this. So after whitening, as you see, whitening is an important step. After whitening operation, we can use the previous results for uncorrelated noise. So this is what we do in general. We always apply whitening, and then after this whitening operation, we analyze this problem and we get a solution for it. Okay? So this is like a conceptual simplification of the analysis. So after whitening operation, we can use previous results for uncorrelated noise case. Okay? Meaning that this result, I want to use this, and I want to use maybe this, okay, for this. Okay, then W, let me say hat of this, with the new problem, this problem is equal to, this is sigma C square, well in this problem sigma or C is remaining as the same C, divided by sigma C square, but in this problem I have P hats plus 1 times P hat, okay? Of course, this hat is something artificial. Now you can say that, let me insert the P over here. Okay, so what is the norm of this? This is P Hermitian Cn minus 1 P plus 1, okay? So please remember this is P hat Hermitian times P. So it's Hermitian of this. Okay. P Hermitian times Cn minus 1/2 times this matrix one more time. Cn minus 1/2 times P. So I get this. So as you see, I'm expressing everything in terms of original variables of the problem. Okay? So weights are according to this. So what's my estimator? Let me erase this. Oh, okay. Let's say that estimator for this. C hat. Let me put double for this in order not to get confused with the estimator. Double roof. Okay, something like that. And over here. So this is the estimator. Then I'm using this with my double roof variable times double roof observations. Okay, because this is my new model. Then what do I get? I get this result. Let me write it over here. Okay, times P Hermitian times I have X double roof over here. So this part is this Hermitian. So as you see, I have over here. So if I write this one also, Cn minus 1/2 X whitening, then I get my final result. So this is my final estimate. Of course, when this covariance matrix is identity, this is identity, I get this. Okay, that is it. So from this example, we see that when this covariance matrix of the noise in this additive noise model, if it is not identity, then I can always do this whitening operation. And this whitening operation is nothing but inclusion of the C inverse matrices, covariance matrix inverse matrices at the processing points. What are the processing points? So this is like related with the whitening part. This is related with the signal model after whitening and so on. So once you have enough experience in these problems, these kinds of calculations always come up. Okay? But the important conclusion may be, it's not the details of this calculation, but if I work with uncorrelated noise, if I understand this uncorrelated noise problem well enough, then correlated noise problem is nothing but the same problem after whitening operation. Okay? So that is the result. Okay. Okay, now let me give you a mini assignment. Set P is equal to one vector, all ones vector, 1, 1, 1, and Cn is equal to a diagonal matrix, sigma 1 square, sigma wn square, and compare the result, let's say this, let's say star, with what was that? X of n is equal to C plus W of n. Example. In the previous lecture, in lecture number 33, we had the solution of this example. So as you see, this is much more general. But if I set P vector as one vector, and this covariance matrix as a diagonal matrix, according to this, I should be getting the same result, isn't it? So just do this calculation and also compare the MSE values. So what is the MSE value of this estimator in the general form and in the specific form that we have previously derived. Okay, so that's a mini assignment. So what else? Okay, so I will cover the next example in the next lecture, and that's all for today. So thank you very much. So we will continue with more MMSE estimators in the next lecture. Thank you.